Swayam Prabha. Digital India. Educated India.
So, good morning again. So, one more lecture which is in some sense similar to what we had yesterday on singular value decomposition, but also different in certain important ways. Okay. Again, handwritten slides, if you cannot read it anytime, feel free to come forward during the talk in between, I won't get disturbed, always feel free to walk to the front if it is not readable. Okay. So, this is last time the singular value decomposition was a very carefully chosen low dimensional subspace. Okay. In fact, the phrase I want to underline is that SVD is a very carefully chosen subspace. You have this singular vectors V1 to Vk in the sense that if you stop it at some 3 vectors V1, V2, V3, you get the best fit 3-dimensional subspace for the data. If you stop it at 6, then you get the best fit 6-dimensional subspace for the data and so on. Now we are throwing all caution to air, okay, and we are going to study what happens if we just take a random k-dimensional subspace and project the data into this random k-dimensional subspace. What happens? Okay, that's why the subtitle for the talk is how good is a random home. Yesterday the subtitle for the talk was which is the best fit low cost home. Okay. So, the low cost still remains the same. We are always looking for dimensionality reduction because data in very large dimensions means lot of computation on all the further processing that you do. So, once usually this dimensionality reduction happens as the very first step after maybe some denoising or whatever. This happens as a pre-processing step. If you can represent in your data in a lower dimensional space, all your computations will dramatically speed up. Okay. So, the low cost still remains the same. What is different from SVD is that SVD was a carefully chosen low dimensional subspace. Now, this is the other extreme. It is a randomly chosen k-dimensional subspace. We will have to again formally define how to randomly choose a subspace, but we will see that. Okay. So, the initial setting remains the same as yesterday. You have n data points x1 to xn in a d-dimensional subspace. Okay. So, I will stick to the same symbols we used last time. Each x1, remember, is a vector. Okay. x1 is not a scalar, x1 is already something like x11, x12 comma x1d. It is itself a d-dimensional vector. You have n such d-dimensional vectors, right. Remember that each of this is something like x11, x1d. And for this to work, we need this usually when do you use a random projection? Okay, you only use it when the dimension that the data is embedded is extremely large. Okay. So, if you have something like n points, and if the dimension is already comparable to log of the number of points, you are not going to get any benefit by using this random projection, because after our analysis we will see that for random projection to work, you need something of the order of these many dimensions, what you see here. Okay. The subspace onto which you are going to project, the loco subspace, is going to have a dimension roughly 1 over epsilon squared log n. So, if your initial space was already comparable to this, there is no point in doing this. In fact, that is why these kind of a random projection is relatively new. The first time this was studied was around 1984. Compare it with SVD, which was available from 1874 and so on. So, this makes its use felt only for extremely large dimensional data, which has become common only recently. Your document term frequency vector, for example, is a classic example of a very large data. Okay. Similarly, audio files and so on. I heard that all these Spotify kind of apps use these kind of tricks to figure out which song you will be most likely to hear based on what you have already heard and so on. So, this is a relatively new technique, much younger compared to SVD. Right. Okay. So, the setting is the same. The only thing that you have to keep in mind extra is that some of our very pretty pictures that we discussed, like the Milky Way galaxy, which is how do you approximate the 3-dimensional universe on a 2-dimensional plane, those you can still ask in this setting, but it won't make that much of a sense. It usually makes a sense only when you are talking about like dimension at least 100 or so, not in dimensions 2, 3 and so. Okay. And what is going to be our key step? The original version of the Johnson-Lindenstrauss lemma essentially picked a random k-dimensional subspace. We will see how such a random k-dimensional subspace can be selected. K is still much smaller than D, and you consider this projection x onto this random space. This is this x with a vertical bar of a subspace we had already used in the last class. This denotes the projection of this vector onto this subspace Rk with some scaling. Okay, don't bother about this root of n by k. You have to really scale it so that something good happens. Okay, so this is the operation that you do. This is the random projection operation that you do. And what is the guarantee that Johnson and Lindenstrauss proved? They said that if this k, the dimension of the target subspace onto which you are projecting, is relatively high, and that high is quantified in terms of number of points and the accuracy you want, accuracy being captured in epsilon. So, it is if it is roughly more than 1 over epsilon squared log n, then something really good happens. What happens if the dimension is at least this? Then for every pair of points in your data sets, there are n points in your data sets, so you have n choose 2 pairs of data points. For every such pair of data points, their distance is approximately preserved. Okay. So, what do you mean by distance being approximately preserved? If x and y were at a distance 1 meter in the original space, then after you do this projection, they will be within 1 plus or minus epsilon meters. Okay. It will be at least 1 minus epsilon meters and at most 1 plus epsilon meters. If it was 10, if the distance between some x and y was 10 meters, then it is going to be at least 10 times 1 minus epsilon, okay, 10 minus 10 epsilon, and at most 10 plus 10 epsilon. Okay. I am saying these two examples to emphasize the fact that it is a multiplicative approximation, not an additive one. Okay. The error that you will incur is also proportional to that original distance between those 2 points. Okay. So, the new distance, which is this guy here, is within 1 plus or minus epsilon of the old distance, and this happens for every one of these n choose 2 pairs. Okay. So, all pairwise distances are approximately preserved, and since it is a random projection, this is not a definite event, we will claim that this property happens with a very high probability. Okay. So, let me repeat, what is the guarantee that Johnson's Lindenstrauss lemma gives you? Tells you that okay, you select a subspace, k-dimensional subspace at random. You don't have to do all those beautiful things you did with SVD, just select a subspace at random, but provided its dimension is high enough, then every pairwise distance in your data set is going to be preserved with within some epsilon accuracy with very high probability. That is the guarantee. So, there is some loss of accuracy, and then there is some randomness in the answer. There will be a very negligible probability that this won't happen. Okay. So, this is the claim. Now, this was the original setting, but maybe I will talk about how to prove the lemma in this setting towards the end. Okay. But 5-10 years later, nowadays this is usually stated in a slightly different version, not a big difference, but what is different is there in red. Okay. The setting remains same, you have n data points in a d-dimensional space, it makes sense only if d is really large, and instead of taking this k-dimensional random subspace and projecting data onto that, you do something which is nearly the same operation. Okay. It is almost like taking a projection onto a random subspace, but not exactly. how much they differ and so on, we will discuss at the end of this lecture. Okay? But this is the modern or the newer or easier to analyze and easier to implement setting of this random projection. So, what you do is you design a matrix, you do not design, in fact you randomly generate a matrix A. This matrix A has, it is a k by d matrix, so you have k rows and d columns. Okay. Each entry in this matrix is a random variable. It is an independent Gaussian with 0 mean and unit variance. Okay. So, I hope you are all familiar with the Gaussian random variable, right, the bell curve, that famous bell curve. So, each entry in this matrix is going to be a Gaussian random variable whose mean is 0 and variance is 1. Okay. That is what I mean when I say standard Gaussian. I will recap some of the useful properties of standard Gaussian in the couple of slides later. Okay. So, this is a matrix now. Okay. It is a completely a random matrix. Every entry is independent of any other entry and each entry is a Gaussian, 0 mean, unit variance, Gaussian. And instead of doing this projection and so on, all you do is you take your x, your data point, any data point, and multiply it with this matrix. Okay. So, your result is nothing but Ax. Again, forget about the scaling 1 by root k etc. for now. That is just so that the distances are all scaled up to what they were earlier. Okay. So, now this whole projection business, projection also can be represented as a matrix multiplication, but then you really have to have a very careful algorithm to pick a uniform random subspace, to pick a random subspace uniformly from the all possible k dimensional subspace, but this is much more standard. You can implement it in a computer very easily. You just have to generate k times d standard Gaussian random variables, all your package, MATLAB, Python, whatever will have a way to generate that many independent Gaussian random variables, right. So, now the transformation has become way more simple. All you do is you generate this random k by d matrix and multiply your data with that. That is going to be the embedded version of your data point. Your x1 will be at 1 by root k a x1, your x2, the second data point, will be at 1 by root k a x2 and so on. Your xn will be at 1 by root k a xn. Okay. Since the matrix is going to be like a long rectangular matrix, the result is going to be just a k dimensional vector instead of d, and since we assume d is much larger than log n and so on, and k is going to be roughly order log n. So, this is going to have a compressed representation of the data. Instead of each data point being d dimensional in the original setting, we will reduce it to it being k dimensional. Guarantee remains the same. Once your k is large enough, the subspace, the k is large enough, then all pairwise distances, all pairwise, okay, all the n choose 2 pairwise distances are preserved within 1 plus or minus epsilon accuracy. Okay. In this, I have, instead of saying distances are preserved, I am saying the squared distances are preserved. That is again the same trick, that makes the analysis easier. That square root in the Euclidean norm is only an annoyance, right. So, it is the same guarantee. If the squares of a distances are preserved within 1 plus or minus epsilon, its square root is also preserved within similar accuracy. Okay. So, that is, so this is the setting that we will discuss more. Okay. Originally the idea came as a projection, but later it's now stated as a linear transformation onto a smaller dimensional subspace. But it is still good to visualize, for our visualization, it is still good to think of it as projecting it to a subspace. Okay. And it is very close. We will see why this particular matrix is almost like projecting into a random dimensional subspace. Okay. So, some remarks before we go further, some surprising remarks. Okay. First of all, this function, this 1 by root k a times x, which is what I refer to as f of x. Okay. F of x is just this function here. Okay. This function here is independent of x, and that is where it dramatically differs from the singular value decomposition. SVD was something which was very much data dependent, but this transformation is data independent. So, it has no understanding of the data, unlike SVD. In fact, SVD we said was still one of the best tools to understand the major correlations, the major patterns in your data. This is completely unaware of the data, because you are just selecting a random matrix, that is your function. You really did not look at the data when you were populating this metrics. Okay. So, this random projection is not really going to improve your understanding of the data, but it is still going to make all your algorithms faster. It is a very good representation technique. It will not give you any insight into the data, it will not tell you anything that you did not know about the data already, but it is a tool to really have a very low cost representation so that your algorithms everything become faster. Okay, that is the first remark I wanted to say. Another surprise is that the required dimension k for which all these guarantees will hold is independent of the ambient dimension. Okay. It only depends on n, the number of data points, and the accuracy you want, epsilon. Okay. That is also in some sense a bit surprising. Okay. So, that way this is really scalable, you really do not have to, your topic vector can have all the 100,000 words from your dictionary, it does not really matter. Okay. The dimension that you will require is only going to depend on epsilon and log n. Okay. And again, this log is an amazingly vanishing function. Think about number of data points being say 1 billion, 1 billion is what, 10 to the power 9, but still log to the base 10 of that is still only 9, right. 1 billion, once you take a log, you will get something like 9 times log 10 to the base 2, which is roughly like what, 25 or 30. So, this log n is really small. What is going to hit you most of the time is the accuracy that you demand, because even if you want 10% kind of, you can tolerate 10% error, that is saying you can tolerate an epsilon of 0.1, which still would mean you need 1 by epsilon squared will be like 1 by 100, sorry, 1 by epsilon squared will be like 100, right. So, that is still going to be the dominant term. Okay. And there was a lot of research on checking whether this 1 by epsilon squared can be improved to 1 by epsilon or so on, but now we know that this is tight. Okay. This is a very recent result, as recent as 2017, where it was shown that in fact this is not just an upper bound, you really cannot go below this 1 by epsilon squared log n is really needed for guaranteeing this preservation of all pairwise distances within 1 by epsilon squared. Okay. And yeah, this also I already mentioned, and also I want to stress the fact that we are not saying most of the pairwise distances are preserved. What we are saying is that all the pairwise distances are preserved most of the time, where the most of the time is another way of saying with very high probability. Okay. Yeah. So, with this remarks, yeah, okay. Before getting into the crux of the matter, let us also talk a bit about applications. I have already kind of hinted what are these applications. Again, remember, all these applications are there, are there even though we know that this random projection has no understanding of the data. Okay. It is something which you can blindly do on the data. There are advantages to it, because like the most common, one of the very common search in data is you represent your data in some database, a query comes from outside, you want to find out which are the nearest points in terms of this query. What are the best matches in your data set for the query that is coming in, right. It is a very common setting. You can imagine 100 applications where you will want to find which is the nearest data point to the query, right. Now, since it is a random transformation, it does not look into the data, it is good, because you had anyway no option to look at the query, right. Your query is something that will come in the future. So, it is good that this projection really is data agnostic. So, whatever query comes in, you apply the same, your A matrix is already there, you just multiply it with that, that gives you the low dimensional representation of the query. Now, in this low dimensional representation, your query is in the low dimensional representation, data points are all in the low dimensional representation, find the nearest neighbor. We have already a guarantee that these distances are approximately preserved. So, the nearest neighbor search in this low dimensional space will almost lead you with the nearest neighbors in the actual space. Okay. So, yeah, this having no understanding of the data is in some cases good, like especially when some of the data is unknown to you. Okay. But keep in mind that it only works if your algorithms only use pairwise distances, right. Like we are not claiming that some other property of the data is satisfied. Okay. So, these algorithms that should use this as a pre-processing should be those algorithms which only rely on pairwise distances, and it is tolerant, it is robust in the sense that it is tolerant to some amount of approximation to this distance. If some algorithm is critical about the distances being matched exactly, then doing a random projection as a pre-processing may be a bad idea. But even with these two constraints, you still have a lot of examples where you do this as a pre-processing, like nearest neighbor query, clustering. If you can imagine, clustering of data points, you can see that both the above conditions are satisfied there, right? What comes in the same cluster is only dependent on pairwise distances, and it's okay if there is some error in or some approximation happening to these distances. So, you can do random projection before you actually do a clustering, and your clustering will dramatically speed up. If you know what are support vector machines, these are ways to classify data into, like, labeled data into good and bad. You find a maximum margin separating hyperplane, but again the idea is very geometric. You have to have the +1 labeled points and the -1 labeled points, the good points and the bad points, let me call them, separated in some way, which is something about their distances. So, that is also a algorithm which only needs pairwise distances and so on. More precisely, it only needs the distance between the convex hull of the 2 points. So, those kind of things are already preserved under this transform, at least approximately. So, in fact, using this JLL together with support vector machines, and if you already know of it, using kernels and so on, is also a very successful line of research. Regression also, when you are fitting a best fit line through the data, you can first pre-process it like this. Ravindran already spoke about this locally sensitive hashing, where I don't know how many of you, because he just in passing he made a remark that actually what you do is multiple random projections, and then instead of retaining the projected vectors in their real sense, you just retain their signs as +1, -1, but now you do multiple random projections. Okay, that will give you a locally sensitive hashing. So, all these applications are there for this technique. Okay. So, now any questions so far? Okay, so far we were at the surface. Now we are going to dive deep. Okay, we will see why this is true. Why should a random projection preserve all pairwise distances? Okay, looks very counterintuitive, right? You did not even look at the data. You just took a random projection, right? And still all pairwise distances are preserved. Okay. And the one line answer to this is that it is really something which is very similar to a law of large numbers. When you average a lot of things, the result tends to concentrate around the mean. Okay. So, this is this is entirely the reason for this happening is entirely a concentration of measure phenomenon. You have, I mean, it's good that we are on the last day also we are seeing something which was probably elaborated during the first 3 days of this workshop, right? You would have seen many algorithms where you first analyze the expected value of a random variable and then see how much is this random variable's behavior, how much is it likely to be in a small window around the mean. Okay, these results are called concentration results. You would have seen the Markov inequality, Chebyshev inequality, which gives you very weak forms of concentration, and you would have also seen the Chernoff. Did you prove the Chernoff bound by any chance? So you use that e to the power moment generating function. Yeah, so that Chernoff bound gives you a way better concentration. It gives you exponentially decaying probabilities for the random variable to deviate much further away from the mean and so on. And this Chernoff kind of inequalities as opposed to Markov and Chebyshev applies in a context where you add up a lot of independent random variables. Okay. When a lot of, this is the law of large numbers in some sense, when you add up a lot of independent random variables, the resulting random variable is going to be very highly concentrated. It's almost another very vague way to see this is if you have seen this result called central limit theorem. It says that under some conditions, if you add up a lot of random variables, the result will start looking like a Gaussian, and this Gaussian is in fact a very nicely concentrated distribution. Its concentration around the mean is very good. It has exponentially decaying behavior once you go further away. So, this amazingly, this seemingly geometric fact, about a random projection preserving pairwise distances approximately, turns out to be a consequence of concentration of measure. Okay. So, that is the one line answer. I would not give you all the detailed calculations, but I will walk you through the key steps, so that your understanding about why this happens is clear. Okay. Yeah. So, yeah. So, we will start with the basics. Okay. Let us have a quick recap of what is a one dimensional Gaussian random variable. Okay. So, you have this particular very famous function, okay, which if you plot it looks something like the picture here, and this function, if this function becomes the probability density function of a random variable, then that random variable is what we call as a one dimensional Gaussian. Okay. This mu sitting here is the mean of the random variable or the expectation of that random variable, and oh, I forgot pi 2 sigma square. Okay. And the sigma squared is the variance, sigma is the standard deviation. This is a fairly easy to study. The PDF looks a bit clumsy in the beginning, but it's a very good, it has very good analytic properties and so on, right. Anybody who is seeing, who hasn't seen this before? Oh, you haven't seen the Gaussian. Okay, then we should talk a bit more about that. Okay. So, first of all, we should know that. It's okay, right. So, first thing to note about this is that it is a continuous distribution, unlike a coin toss or throwing a die. In a coin toss or throwing a die, you have only some finitely many possibilities, but this is a continuous random variable in the sense that it can take values from a continuous set. In this particular case, it can take any value between minus infinity and infinity, but not with the same probability. The probability kind of varies in this fashion. Okay. But what is drawn in this picture, this is again a very common mistake that everybody makes in an interview. What you see here in this graph is not the probability, it is the probability density. In order to, there is no point in asking what is the probability that this Gaussian will take value 5. What is the answer? 0, because it is a continuous random variable, any particular value it will take a probability 0. So, only reasonable question to ask is, you fix an interval on the real line, like say between 5.1 and 5.2, and then you can ask what is the probability that this Gaussian random variable will take a value in that range. That you will get by integrating this curve in that range. The area under this curve between 5.1 and 5.2 will give you the probability. So, in particular, the height of this curve can be much larger than 1. Okay. It is a density, it is not like a probability which is at most 1. So, the mean in this case also happens to be the highest point in the curve. It is not necessary that every distribution has that property. In fact, the peak of the curve is called the mode. So, in Gaussian it happens that the mean and mode are the same, and something like 68% of your probability is within some mean plus or minus 1 standard deviation. Okay. So, it is a very good thing. In fact, if you go to something like 3 standard deviations, I think almost 99% of the data of the probability is within some 3 standard deviations on either side of the mean, and so. It is a very well concentrated, though the picture does not look so, it is a very well concentrated kind of a distribution. And when you say that a random variable is Gaussian, all it means is that its probability density function is this. Okay. And do not worry if this this f of x, this expression is going to look a bit clumsy and so on. In fact, we will only use a special case of this Gaussian called the standard Gaussian or the standard normal, where the mean is 0. So, this peak will be at the origin, the curve will be shifted to the origin, and the variance is 1. Okay. So, that is the standard normal distribution with which we will be mostly spending our time. Okay. This is the one dimensional Gaussian. We already mentioned that its mean is mu and its variance is sigma squared. Okay, but these are some things which you probably always know. I mean, any first time you encounter a Gaussian, these two things you study, the mean and the variance. Okay, this property also you may study, but you may have not paid that much attention. But this is a very, very important property possessed by Gaussians, and it's some kind of a closure. So, suppose x is a Gaussian random variable, then 10 times x is also a Gaussian random variable. Okay. All that the mean remains, if mu was the original mean, 10 mu will be the new mean. Okay. If sigma was the original variance, then 100 sigma, not 10 sigma, 100 sigma will be the, sorry, if sigma squared was the original variance, 100 sigma squared will be the new variance. In fact, the standard deviation scales according to what we multiplied with, the variance will scale according to the square of it. Okay. More similarly, if x was a Gaussian and you add a constant to this Gaussian, it only kind of shifts the curve along the x axis. The result is still a Gaussian, the variance does not even change, the mean gets shifted by the constant that you added. These two properties are together mentioned, together described in the first line. Okay. If x is a Gaussian and you consider something like ax plus b, where a and b are real numbers, constant real numbers, the result is also a Gaussian, the mean and the variance will change as written here. Okay. Second important property is if you have two Gaussian random variables x1 and x2, which are known to be independent. Okay. Remember, our matrix is going to be full of independent Gaussians. If you have two independent Gaussians, you add them up, you again get an independent Gaussian. I mean, you again get a Gaussian. This is a very rare phenomenon. Okay. Not many distributions have this kind of a phenomenon. For example, if you think about throwing a die, okay, the distribution is going to be, the probability is going to be 1/6 for all the 6 possible outcomes, right. But if you now throw two dice independently and then ask about the sum of the throws, okay, then it's no more going to be a uniform distribution. Okay, the sum is more likely to be around the center values like 7, 8 and so on. It is very difficult to get 2 or 12, because you will get a 2 only if both the dice come up with 1. You will get a 12 only if both the dice come up with a 6, which are probability 1/36. But you can get a 7, for example, if the first one is a 1, second is a 6, first one is a 2, the second is a 5, or 3 and 4, or 4 and 3, or 5 and 2, or 6 and 1, right. So, I think there are something like 6 possibilities for this to happen. So, you have 1/6 probability of getting a 7. Okay. So, you add up two uniformly distributed random variables, the result is not uniform. In fact, it will have more like a triangular shape. So, the fact that Gaussians remain a Gaussian even if you add two independent Gaussian is a very critically useful property. Okay. In fact, this is also one of the secret reasons behind why central limit theorem is true. If the sum of a lot of random variables has to converge to something, that something has to be something which does not change when you add it further, right. Because if you are taking a sum of lot of things, the sum of the first half will converge to a Gaussian, the sum of the second half will converge to a Gaussian, which means the total sum is sum of two Gaussians, it better converge to a Gaussian. So, this property that sums of independent Gaussians remain a Gaussian is very important. Okay. Now, let us put property 1 and 2 together and you will get a much general property, because now I am going to say that linear combinations of independent Gaussians is also going to be a Gaussian, right. So, you take this x1 is a Gaussian, x2 is a Gaussian, xk is a Gaussian, and they are all mutually independent. Alpha 1, alpha 2, etc., alpha k are just scale factors, real numbers. You scale them and add them up. While scaling, because of property 1, since x1 is Gaussian, alpha 1 x1 is also Gaussian. Since x2 is Gaussian, alpha 2 x2 is also Gaussian. Now, since sum of Gaussians are Gaussians, this total sum is also a Gaussian. Okay. This is a critical property, irrespective of its use in Johnson, Lindenstrauss and all. Please try to remember this, that Gaussian has this very special property that it is closed under linear combinations of independent Gaussian. Independence is important. If it's not independent, yeah, we can say something, but let's not get into that. Everybody clear? Okay. Now we will take Gaussians to higher dimension. It's not a scary object. It's something, if you haven't seen it before also, it's something you can understand very easily. Okay. Now we are not talking about a random variable, we are talking about a random vector. Okay. Now like any other vector, vector is just in our computer science view of a vector, we have to just think of it as a list of numbers. Okay. So that's a deterministic vector. Now what is a random vector? Each of entry in this list is now a random variable. Okay. So that's what a random vector is. Okay. Fairly easy object to define. Okay. Each entry is a random variable. Okay. Now what is this spherical Gaussian? Each entry is going to be a one dimensional Gaussian. Okay. And moreover, all these one dimensional Gaussians are going to have 0 mean and the same variance. Okay. I will keep it even simpler and I will call it standard spherical Gaussian and I will make that variance as 1. Okay. So the random vector that we are going to talk about, each entry is a standard Gaussian, okay, or a standard normal, which means just that it's a 0 mean unit variance Gaussian. So that is a random vector and this random vector is said to be this is just a name that you give to it, a standard spherical Gaussian in d dimensions. Okay. We will, the standard Gaussian, I think I did not highlight enough. This is the notation that we had used for Gaussian, okay, n for normal. N, the two parameters, the first parameter denotes the mean, the second parameter denotes the variance. So the standard Gaussian will be n01. The spherical Gaussian, in its notation, we have introduced this extra term called d. Okay. It tells you what is the length of the vector you are talking about. Okay. And these Gaussians are independent. Now if you want to study the probabilistic behavior, the statistical behavior of a random variable, in the discrete setting you study its probability mass function, or in a continuous setting like this we study the probability density function. For a random vector, the equivalent thing is called a joint probability distribution. So here the probability distribution, the density will no more be a curve that you can draw like this, but if it's a two dimensional vector, the domain itself will be the plane and the curve will look like a a sheet or a canvas over this plane. Okay. So that is the picture. For a two dimensional random variable, what is the density? Density is no more a function of one variable, it's a function of a ordered pair. So you will have to imagine it as a sheet floating on a surface. Okay. And in the case of a two dimensional Gaussian, it will really have the shape of a bell. Okay. This is in fact, if you can look, oh, I think I moved to the wrong slide, I should have gone back. Okay. If this is the one cross section of a bell, you think of rotating it around and you complete the whole bell, like the church bells that you see on top of some old churches. It's that shape of a curve is what will be a two dimensional Gaussian. Imagining a three dimensional Gaussian is tricky because you need a four dimensional imagination to imagine a three dimensional Gaussian, because the domain is already three dimensional and the density is another real number which you have to represent somehow. Okay. So imagining, visualizing is hard, but roughly this is what a high dimensional Gaussian is. Okay. And you also know, again I will not go too much into these, once you have independence, then the joint distribution is very easy to find. It is going to be the product of the marginals, product of the individual distribution. So if you know, since you already know the distribution of a one dimensional Gaussian, which we had in this slide, all you have to do to find that of a two dimensional Gaussian is multiply fx of, let's say, what is the joint distribution at some point x1 comma x2, it will be this function at x1 times the same function at x2, because it's the same function, right. So if you, that is what, and if you like write it out, you will get this, right. So maybe I will try to, so this was, this first guy here will be something like 1 by root 2 pi there should be a sigma, but sigma is 1, and then e raised to minus x1 minus mu, but mu is 0. So, minus x1 squared by 2 sigma squared, but sigma is 1. So, by 2. This is what fx of x1 would be. What would be fx of x2? The same thing, 1 by root 2 pi e raised to minus x2 squared by 2, and so on. What would be this guy? 1 by root 2 pi e raised to minus xd squared by 2. Now, if you multiply all of this, this root 2 pi comes d times. So, that is where you get the 2 pi to the power d by 2, or it is root 2 pi to the power d. And what happens to the things in the exponent? E raised to a times e raised to b is e raised to a plus b. So, everything gets added up. So, it will be e to the power minus of, this is 1 by root 2 pi to the power d, and e to the power, let me pull this minus half out, and then you will get x1 squared plus x2 squared plus etc. xd squared, right. What is that? x1 squared plus x2 squared plus 0, that is a norm of x square. Okay. So, that is why we have written it as, in the norm form, okay, norm of x squared. Okay. So, you should never try to, why I did this derivation is to tell you that do not try to remember all these complicated expressions. The single dimensional Gaussian you have to remember, you just have to multiply it with putting the appropriate arguments x1, x2, etc. instead of x to get what this is. Okay. So, this is the spherical Gaussian, the higher dimensional Gaussian. This is not the most general higher dimensional Gaussian. You can have dependent variables also, in which case something will get slightly more interesting. Okay. Now, this particular Gaussian, the spherical Gaussian, has a very useful property, which is that if you look at its joint distribution, it is a function of this vector, right, x1, x2. The x that is here is in fact a vector x1 is a d-dimensional vector. Okay. So, f of x, the value depends on x1, x2, x3 and up to xd, true, but the dependency is only via the norm of the vector x, right. If you look at the thing, right. So, if you think about two vectors with the same norm, okay, the density is going to be the same there. So, let's say do this imagination in 2D. Okay. So, what are all the vectors whose norm is 1? The points on the unit circle. So, now if you imagine the Gaussian density curve, the two-dimensional spherical Gaussian density curve, along this circle the height is going to be the same. Okay. So, if you do a contour plot, you are going to get this unit circle. This distribution is going to be the same, of the same height at the unit circle. Now, look at all the points whose norm is 4 or 2, right. That would be a circle whose radius is 4 or 2. There also the height of this density is going to be the same. So, there is this circular symmetry that you see. Okay. Another way to visualize it is that this bell, if you kind of rotate around the origin, does not change. Okay. It has this circular symmetry. Okay. This only happens because all the components were of the same variance and independent. If the second dimension had a larger variance, this bell will look like it is stretched, it is elongated on that second dimension and slightly shrunk on the first dimension. But since it is all the same variance, you have this circular symmetry in 2 dimensions, or more generally you call it a spherical symmetry in higher dimension. In 3 dimensions, what we are saying is that you cannot really imagine the plot because the domain is already 3D, but all the points on the surface of a sphere centered at origin of whichever radius. Okay. But once you fix the radius, all those points are going to have the same density. This is why it is called spherical. Okay. It is in fact, it should have been more elaborately called a spherically symmetric Gaussian, but since that is a very long phrase, people call it a spherical Gaussian. Okay. So, at least the 2-dimensional spherical, do you have it in mind? It is a very circularly symmetric bell, like a church bell you can imagine. Okay. Now, because it is spherically symmetric, there is lot of use to this spherical Gaussian. Like for example, if I want to sample a uniform direction in 3D space, okay, I want to sample, which is essentially saying I want to sample a unit vector which could be which is uniform on the sphere. Okay.